Okay, kids, we're back with the next idea here in our last unit. It's called electromagnetic induction. Now, there are two other videos that I really want you to watch before we watch this video lesson. It'll just make the video lesson more relevant to you. It'll make the video lesson more relevant to your learning. So please, please, please watch those two videos in order. I think it was the sixth segment of the one we've been watching for a while. The cartoon one, and then since I can't do labs for you, with you and demonstrations for you, I found a real life magnet demonstration. I think it's from a professor from a university in the United States of America. So watch those first. So electromagnetic induction. Here we go. I want you to remember something, that you can have an electric field, and that electric field surrounds a charged particle like an electron. And here are the arrows that represent an electric field. Now, if this charge moves, if the electron is moving, it has a certain velocity, for example, like an electron moving in a wire in a circuit, then it's going to drag its electric field along with it. So the electric field is changing, delta electric field. And what have we learned? We've learned that if there's a changing electric field, it produces a magnetic field. Well, when did we learn that? Well, when there's a current in a wire. What does that mean? Current in a wire or a coil. What does that mean for there to be a current in a wire? It means an electron is moving, dragging its electric field along with it as it's moving, and therefore the electric field in a vicinity in space starts to change as electrons slip past it. The electric field dragged along with it. So in the area in the volume where the electron is moving, the electric field is changing. And what did that lead to? It led to a magnetic field. Anytime you've got wire or a coil and it's got current in it, you've got a magnetic field. Now we kind of want to look at this in reverse. Now what we want to say is, look, here's a bar magnet. And look, I've drawn the magnetic field with it. All right. I want to now move the magnet. So if I move the magnet here, the strong part of the magnetic field is here. But if this magnet moves through space, this strong magnetic field will travel through different coordinates. So those coordinates will experience the coming in of the strong magnetic field. It's moving towards, let's say, this area right here where the V is. Oh, a magnetic field, a strong magnetic field is coming towards this space. That means the magnetic field in here would be changing. And then the rest of the bar magnet goes through. Oh, now I've got these areas coming through where there's less magnetic field lines. So this area would be experiencing a weaker magnetic field. There's been a change in magnetic field. And then the south-seeking pole would pass through here. So then all of a sudden the area here has a strong magnetic field again. Regardless of all these details, as the bar magnet moves, it drags its magnetic field along with it. So into the space that it moves into, the magnetic field is changing. Well, if this changing magnetic field is near a conductor, it will produce an electric field in that conductor that will push along a current. That will push along a current. So you kind of got this symmetry here. If you change the electric field, right, by moving a charged particle, a magnetic field is produced. But if you change the magnetic field by moving a magnetic field around, like moving a bar magnet around, then that produces a change in the electric field. And if that changing electric field is near a wire or a conductor, bingo bango, we're going to get a current. Now, who worked on that? Well, a guy named Faraday in England and another guy named Henry in the United States worked on this. And they came up with Faraday's law of electromagnetic induction. It's named after Faraday instead of Henry because he published it first. So he gets credit for it. That's the way it works. He wrote a paper for it first. He's brilliant experimental scientist. Oh my God, unbelievable. So whenever a changing magnetic field exists near a conductor, near a wire, or near a coil, a current, there's the symbol for current, is induced in the conductor. So the magnet itself is not touching the wire or the coil. It's being moved around near it. That's why we have the word induced. If it was touching it, it would be contact or conduction. It's not. It's near it. It's induced. So that's what the two of them figured out. What they did not figure out, well, okay, thanks a lot there, Mr. Professor Faraday and Professor Henry. I appreciate it. But can you tell me the direction of the current that is produced? Well, they didn't do that. Another really smart guy, Lenz, Lenz. That's his last name. Lenz's law. He came up with the direction of the induced current. He was able to figure that out. So this is what he said. He said, for a current which is induced in a conductor by a changing magnetic field, the induced current is in such a direction that its own magnetic field opposes the change that created it. So here we go. Let's take a look at this step by step. Step one, move the magnet. So here is a coil. I've drawn a coil for you here. There's the wires going around the coil, and there's a galvanometer, which measures tiny charges. Here's a bar magnet. We're going to move the bar magnet towards the coil. Well, according to Faraday's law, if you move a bar magnet, you're moving its magnetic field along with it. So this conductor, known as a coil, is going to experience a magnetic field coming towards it, right? Pretend this bar magnet's going in. This coil is going to experience a magnetic field going towards it. Therefore, it's experiencing a changing magnetic field. And that's what I wrote here, a changing magnetic field near a conductor. In this case, it's a coil. So this coil experiences a changing magnetic field. And what Faraday taught us was, well, if you've got a conductor, in this case a coil, and it's experiencing a changing magnetic field, a current will be induced in the coil. So this coil will all of a sudden have a current moving through it. And I hope you watch those two videos. Well, kids, if you've got current moving through a coil, it's going to have a magnetic field created. Anytime you get current moving through a conductor, in this case a coil, it's going to create its own magnetic field. And that's what I wrote here. The coil has its own magnetic field now because current was created. But I still haven't answered what is the direction of the current, because the current could be going up and then into the page and down, out of the page, up, into the page, and down. You don't see the wire, it's behind the structure. Down, up, towards you, and then back up again. That's a possible direction, but it could just as easily be the other way. What's the right answer? Well, it all is dealing with this word right here, opposes. The current that is created in here creates a magnetic field that tries to stop or oppose the change that created it. So it's going to try to stop this north-seeking pole from entering. Well, the only way you can stop a north-seeking pole from entering, or try to stop it, is by repelling it away. The only thing that will repel a north-seeking pole is another north-seeking pole right here to try to repel it away. So you have to put a north-seeking pole here in order to oppose the north-seeking pole that's coming in. And then by default, you have the south-seeking pole there. So now we have the right-hand rule for coils to find the direction of the current. Remember the right-hand rule for coils? Well, you're using it, but you're using it backwards. When we used it before, we knew the direction of uh, the current, right? And then we were, so, oh, I know the direction of the current. I know where the north-seeking pole is. Now it's in the other way. I know I had to have a north-seeking pole here in order to oppose that north-seeking pole from coming in. So you start with your thumb there now, right? Oh, I got to oppose that north-seeking pole from the bar magnet from coming in. So I got to repel it away with another north-seeking pull. I better put my thumb right here. So you put your thumb there, and then your fingertips curl in the direction that show that the current in the coil is definitely up here in front as I've drawn for you. So it's still the right-hand rule for coils, but instead of starting with a current first and then establishing where the north-seeking pole is, now you start with where the north-seeking pole is to establish the direction of the current. So there you have it, kids. Okay, so keep on working. Don't fall into bad habits. Every day work. Every day do something. You want to really have the good habits of a good, regimented, ordered, disciplined student. Yes, this physics stuff is important if you're going into, the areas of math, technology, engineering. I get it. It's important for your future. But I'm telling you right now, what's more important is discipline, order, regiment, forming good habits. I know it's not easy right now. It's tough out there. I get it. This is different. It's not as easy as it was in the past. I understand that. I wish I could change it, but I can't. But stick to it. You're a teenager now. This is when you are starting to form the habits that will be with you for the rest of your life. Keep learning, keep working hard, keep pushing. I can't do that for you. That's on you. All right? We're talking about your future here. You want to form good habits. Form good habits for your own sake. Remember, I used to be a student. I used to be a physics student at Stanford Collegiate when I went to Stanford. Great school back then, great school right now. All right? I had friends that were lazy, didn't want to do anything, came up with an excuse all the time not to do anything. I'm still friends with them. They're struggling. Bad habits were formed. Stayed with them for the rest of their lives. Don't do that.